So I hope the PSAT is going well for you. You're going to be recording these notes on types of bonds. We're doing covalent bonding. And what I need you to do is, now at this point, I already went over this, so you're going to have to pause the video when you're watching it. And let's get these definitions put in for a covalent bond. So when atoms share electrons to be stable. It's when a nonmetal bonds to a nonmetal. It's when valence electrons are shared in pairs. So pause the video right now and get that drawn. Okay, so what happens here is that those two hydrogens are going to move towards each other, and they're going to share those two electrons. Now we've got a pair of electrons being shared. Each element there, each hydrogen, thinks it is now helium, and you get a fairly stable chemical bond. So that was part A, covalent bond. Now we're on part B, down here. Types of, and that's for the rest of you. Now we're back over here. Thanks for working with me on that. So types of covalent bonds. We have the single bond. That's going to be one. It's going to be one pair of shared electrons. So for an example, let's do a Lewis structure for methane. This element here is methane. Okay, I guess I need to give you a moment to write it out. So types of covalent bonds, single bond, two shared electrons. Oh, methane. I forgot the H. Sorry about that. Oh, that's embarrassing. Now, we're all familiar with methane. Methane is the gas that's produced if we mammals have too much beans and sometimes fruit, because the ribose sugar in that doesn't break down like the regular sucrose sugar that we eat. So you end up getting little bubbles of methane formed inside, and they come out with funny results. So there is carbon's Lewis structure. And then we're going to draw in the four hydrogens that come along for the party here. And I'm going to put their shared electron just as an X so that we can see. So we end up with a fairly stable compound. We've got some energy stored. It took a little bit of energy. The organism that made this, it had to expend some energy to do this. Now, these can be broken. This is the simplest of the natural gases, and this is a fuel. As some of my college roommates learned that, yeah, that stuff really does ignite if you light it with a match. Okay, but it can burn as well, okay? And so be careful, I don't recommend it. Don't do it. You know who I'm talking to over there, okay? So, let's go. So, now, we're going to redraw this. Again, now we're going to put carbon over here. So a lot of times, as a shortcut, chemists don't want to draw the Lewis structures because chemists are lazy. Hey, we know that. Look at the periodic table. They made symbols for everything, okay? They're lazy. So instead of drawing those two paired electrons, they'll just do this. They'll make that dash line. Now if you want, you can put little dots at the end, but they don't do that. So for methane, you'll see sometimes diagrams, or if you watch, some of those crime shows, they'll put some molecule up and there's carbon and all sorts of stuff hooked together with lines. That means a pair of electrons being shared. So there is methane, or laughing gas. Okay, the next one, number 2, the double bond. This is when 4 electrons are shared. 4 electrons are shared. I'm right in the middle of recording. Can you come back in about 10 minutes? Please come back, because I can't stop it right now, or I would. Okay. Thank you. Oh, I think I was going to get a donut, but I don't need one, okay? Anyway, 4 shared electrons. O2. So let's draw the Lewis structure for oxygen. And when we do it, before, we found out that I'm going to put these at a slight angle right there. If that bugs you, deal with it. Okay, so there we go. There's oxygen. It's in group 16, so it's got its 6 electrons. Now I'm going to draw another oxygen over here, the mirror image. We're going to put its 2 paired electrons over there. Its 2 unpaired electrons right here. And then what happens is when these get near each other, they say, hey, I need some electrons. Can I borrow yours? And those 2 electrons will connect together. So we can clean this up a little bit and do that. Chemists usually don't bother putting in the 2 pairs of electrons on each oxygen. They just usually shorten it to that. But that is how we take the Lewis structures and we get them converted into what's called a structural formula. Now, if you prefer something like this, you can do that if you like. This was kind of making it, a couple Lewis structures coming together, joining, and what they're doing here, there's like those two are teaming up, those two are teaming up, and then we've got two pairs of electrons that are being shared. 4 electrons between one atom. When 4 electrons are shared, I got to do it over here. When 4 electrons are shared between one atom, there has to be a double bond. You don't need to draw that if you don't want to, but may I go on to number 3? Have I given you enough time? Yes.
Ionic bonds or double bonds too?
Now the thing is, great question. So the question was about ionic bonds. When you have an ionic bond, to counterpoint this, they're not sharing electrons. So like when we talked about sodium, it has that 1 electron right over there. Chlorine has 7 electrons out there. What happens is sodium gets rid of this. It throws that electron away over here, ionizing this to be negative. Sodium, when that happens, it ionizes positive. So what happens there is they're not sharing electrons. Okay? They've become stable. Now, the price they pay for that is that that plus charge is going to be attracted, it's called electrostatic attraction, to that negative charge. And these two are going to have to stay fairly close together. Okay? In fact, really close together. It's a really strong attraction. It's really hard to break apart a salt molecule. We'll be doing a lab in here where I'm going to give you some sugar, which is a covalent bond. You're going to put it in a flame, and almost immediately the sugar begins to burn and react. When we do the salt, any ionic compound, you may be sitting there for quite a while trying to get it to heat up and melt because it takes a lot of energy. In fact, one of the things they're thinking for storing energy is that when we collect solar panel energy, and a drawback with solar panels are they're only good during the daytime. Well, some people are thinking, okay, if we get these solar panels off in the desert and they're collecting sunshine, what they're thinking is taking that electricity and in underground storage vaults, they're thinking of having salt containers. And it usually is probably in a liquid form. But what happens is they're thinking about taking that electrons, the extras they have, and they heat it up. And so they spend all day heating up the salt material in these underground storage containers, and they get very hot. And then during nighttime, when there is no solar energy, you have a power plant set up over here that takes this hot sodium and then it makes water boil. And water boiling is how we drive that's biology, B-O-I-L. When the water gets boiling, we can hook it to a generator and generate electricity. So there's some works in there about storing the energy we can get during the day in molten sodium and then using that at nighttime to run a generator so we got the power at night. So that's stuff that's going to be happening in the next 10 years more and more as we try to get away from the petroleum economy that we're on. I mean, our economy is driven by burning coal, by burning fossil fuels, and it's polluting the atmosphere, and stuff like this is a way that we can begin to store that energy at night. So anyway, thank you for the question. Appreciate it. Lastly, the triple bond. The triple bond. So this is when 6 shared electrons are going to occur. And then we'll do an example with nitrogen, so I'll give you a moment to write that. So triple bond, 6 shared electrons. And while you're writing that, when chemical reactions occur, and usually like in biological entities, it takes energy to stick 2 oxygens together. It takes a little bit of energy. It stores that energy in there. And that's why when we burn things, we need to have oxygen present, because oxygen has stored energy in here, and the oxygen allows reactions to occur. It's almost like the oxygen kind of acts like an electron sponge that'll strip electrons from, like, say, hydrogen. And so anyway, with the double bond, a lot of energy. Now we're going to triple bonds. It takes even more energy to make these. So we're going to do the Lewis structure for nitrogen on there. So let's do like this, and we'll put it's paired, it's in group 15. So the Lewis structure for nitrogen is like this. We're going to do the opposite mirror image for the second nitrogen that comes along. And then, can you figure out what they're going to do? Hello? Well, quit making googly eyes at him. You got to be focused on this. You can work in the lab and make googly eyes at him, okay? So, okay, which electron is this one going to pair up with? Oh, wait a minute. Oh, I know what your problem is. You're saying, hey, I forgot to put that one, didn't I? Okay, got it. Thank you. Come on, which is this one going to team up with?
The one across.
Okay, the one across from it. Now, actually, it can team up with that one, but it's easier to draw this. So we're going to draw a connection right there. These two will draw them together, and then those two will draw them together. So what happens is when nitrogen gas gets near each other, two nitrogens, you end up with a triple bond. You may see that. Again, that's a very high energy bond. Takes a lot of energy to rip apart a nitrogen molecule. Oh, I guess we should put the two unpaired electrons. Now, carbon can do this too. Carbon, it gets a little weirder. Let's do the Lewis structure for carbon. Oh, this is going to be ugly. Okay, I'm going to stagger this because this is not going to be pretty. Okay, I'm going to do it like this. So, okay, here's what happens when carbon makes a triple bond. This is okay. Those two will come together. Those two will come together. Okay, that takes a lot of energy. Now we're going to connect these two. It takes a lot more energy to connect these two because there are now a whole bunch of electrons being paired next to each other, but it can stay together. Now, this one cannot. Don't draw this. This cannot connect over. I had a student ask me, why can it not make a fourth bond? The electrons are too close to each other. Their negative charges are going to break this whole unstable thing apart too quickly. So what tends to happen is when carbon does a triple bond, it's got a bond with something else, and usually it'll grab a hydrogen out there floating around, and you end up with this, acetylene. Have you ever heard of acetylene? Ever heard of acetylene? Nobody's does any welding, or has anybody that does welding? A lot of the welders will use acetylene gas as the fuel to run their torches because there's a lot of very high energy in here. So that's acetylene. All right, I think we are done with our notes for today. Oh, no, we're not. Part C. Okay. Almost done there. Now, for my students that are not here, I've got these little periodic tables I gave out. They're actually smaller than this one I have here because we're going to do a little deal here. So you'll have to get one of these in class. Part C, then we're done. Then we'll do the lab. Diatomic molecules. What does diatomic mean? Okay, you got 10 seconds to talk to your group members to come up and tell me what diatomic means. Go. Talk to your group members. Talk. Turn. Okay, time's up. What does diatomic mean? Oh, I'm going to be so... Come on. Okay, what does di mean? Two. What does atomic mean? Atoms. You knew that. You were just shy. Okay. 2 atom molecules. It's that simple. So, diatomic molecules are naturally occurring molecule containing 2 atoms of the same element. Now, there are the 7 diatomic molecules. At this point, that little periodic table, you can get that taped in to your paper at this point. So these are the 7 elements that can join together with the same element to make a diatomic molecule. Hydrogen we use for fuel. Oxygen is used to make fuel burn. Nitrogen is mostly what's in our atmosphere, 73 to 76%. When you take a deep breath, you're breathing mostly nitrogen. Now, that's not a problem for us until you go scuba diving. Because if you go scuba diving, and if you go below, I want to say 10 feet or 10 meters, what can happen is that compressed air you're breathing, which is nitrogen and oxygen, you inhale higher concentrations of oxygen and nitrogen. The oxygen doesn't affect us. It breaks apart pretty quick and comes out of our blood quickly, but the nitrogen doesn't. And if divers that have been down deep and fairly deep or fairly long, if they come up too fast, what happens is the nitrogen gas that's dissolved into their blood will begin to pop into bubbles in their blood. Oh, here's your blood vessel. Okay, so it's kind of a bad thing if all of a sudden you come up to the surface too fast and the dissolved nitrogen, because nitrogen doesn't go out of your blood as quickly as oxygen does, pretty soon you got all these bubbles in your veins, and that's going to be really painful. And typically people tend to bend over in pain, and they call this the bends. They're getting too much nitrogen. So divers, when they go down, especially deep, they will rise maybe 10 meters and they stop and they breathe. Anybody a scuba diver? Anybody get scuba trained? Anybody know? Have you done that?
Yeah.
So what's the rule? Tell us the rules for that.
Oh, I don't remember
When you were younger, but do you remember them talking about that? If you go deep, you have to like go up a certain stop for a minute or two or something, and then go up another 10 feet or something. Do you kind of remember that? That's to let this stuff slowly bleed out. Okay, so periodic table now. So what we've got is there are 7 of these, and so with your highlighter, I want you to find atomic number 7. Atomic number 7. Do you see it right here? It's nitrogen. So let me zoom in here. So what we're going to do is, since there's 7 of these, you're going to go to atomic number 7, and we're going to turn this in. We're going to highlight these 3 right there, nitrogen, oxygen, and fluorine. Then we're going to highlight the next 3 below it. And what we end up with, we make a little 7, starting with atomic number 7, like that. There are 6 of the diatomic molecules, and then hydrogen is the other one sitting over there. So when we have the unit test, they may say which of the following can be a diatomic molecule. On your periodic table, find atomic number 7. Outline or make a little 7 on your periodic table. Those can be diatomic molecules, and then hydrogen up there can be as well. With that, we are finished. Thank you for your attention, everybody.